It's my pleasure to introduce Professor Igor Velcic of University of Zagreb in Croatia. He's an expert. He's an expert in homogenization, in the study of the homogenization and thin structure. And he obtained very interesting result for nonlinear elasticity. Now, in the last year, he started to study stochastic homogenization. And now the talk of today is stochastic homogenization of high contrast media.
Good morning to everyone. So the title of the talk is Stochastic Homogenization of High Contrast Media. And this is a joint work with Mikhail Cherdantsev from the University of Cardiff and Kirill Cherednichenko from the University of Bath. Before starting to talk, I would like to thank the organizers for giving me the opportunity to give a talk on this very nice conference. So the outline of the talk is the following. We will give a very short introduction into homogenization. First, we will say something simple about classical non-high contrast homogenization. Then we will speak about periodic high contrast problems. Especially, we will speak about band gap structure of the spectrum in such material. Then we will turn to stochastic high contrast homogenization. And on bounded domain, we will comment the convergence of the spectrum of epsilon problems to the spectrum of the limit operator. Then we will introduce Zhikov's beta function and see what is its connection with the spectrum of the limit operator. Then we will speak about why it happens that on the whole space setting, the limit spectrum of epsilon problems, this set here I will call limit spectrum, is different than the spectrum of the limit operator. Then we will give in the whole space setting the full characterization of the limit spectrum in the case of finite correlations. And then we will speak about the notion we introduced, what we call statistically relevant and statistically irrelevant parts of the limiting spectrum. So when you have operators with periodic coefficients, A is a matrix-valued function, which is Q periodic. And in the beginning, we assume that it is strictly coercive. And then you look the resolvent equation. You know if the right-hand side converges in L2, the solution converges to the solution of the limit problem, which has the same structure as the original problems. But here, A home is the operator with constant coefficients. And the coefficients you can calculate by cell formula given here. So you do it by calculating the corrector on the unit cell, and then you simply calculate, and then you calculate what are the coefficients that are depending on this corrector here. So these are the standard things in homogenization. Okay. Now, if you want to, we want to study the problem when we have, instead of periodicity, we have, in a way, what is statistically periodic. So medium is not anymore purely periodic, but it is in a way statistically periodic. And the framework was introduced in nice lectures by Professor Piatnitsky. Sorry. So you have a probability space and you equip it with a dynamical system, meaning you have a family of measurable bijective mapping and that satisfies the following three properties. The first property is the group property. The second property is measure invariance. It somehow implies the stationarity. It will imply the stationarity of the random coefficients in the sense of distributions. And the third, also very important property, is the property of measurability of this mapping with respect to product sigma algebra, where in the first variable you take the Borel sigma algebra, and in the second variable you simply take the sigma algebra that comes from the probability space. And we will additionally assume that this dynamical system is ergodic. The reason for doing that is that in this case, you will have that the limit operator is deterministic. And ergodicity you can define in two following equivalent conditions. Either you will say that for every measurable mapping that is translational invariant with respect to every x is Rn, if the mapping is translational invariant, then that mapping is constant almost surely. Or if you take the subset B of omega that satisfies that is translational invariant for every x in Rn, then the probability of such set is either 0 or 1. And somehow the basic theorem in the background is the Ergodic Theorem, which says the following. So you have a probability space with an ergodic dynamical system, and you take function which is in LP omega, and then you define its physical realization. So for fixed omega, you define the function in x that is given by f of tx of omega. And then, as Professor Piatnitsky introduced, you impose, the consequence of the Birkhoff ergodic theorem is the fact that these functions satisfy mean value property, meaning if you scale them, they converge weakly to the expectation of the random variable f. So let us just say that for omega in omega, the set Tx of omega, when x goes through Rn, we call the orbit of omega. And this also tells, the consequence of this is also, if you know somehow one typical orbit, then you can somehow construct the probability measure in the background, right? And also, so you call typical omega such omega that this property is satisfies for every f, and if L1 omega is a separable space, which happens, for example, if sigma algebra is countably generated, then indeed the set of typical omega is the set of probability 1. Then, by using this ergodic dynamical system, you can define the probabilistic gradient so you define the unitary group which acts on L2 omega, which acts on the function f in the following way. So this is obviously unitary group since T is measure preserving. And you can show, actually Professor Piatnitsky showed its strong continuity, and thus there exists infinitesimal generator, which is antisymmetric operator. And with these operators, di of f, which are somehow derivatives, you can also define the probabilistic gradients, and you can show if you take a function f, which is in the domain of the probabilistic gradient, and you look at, and then you take its probabilistic gradient and you look the realization of that, that is the same as looking the realization of the function f and taking the physical gradient in the weak sense. By using the probabilistic gradient, you can naturally define the Sobolev spaces on probability space omega. Why is this happening? And then, so how do you model random coefficients? So how do you model the random coefficients? That was also explained, random stationary field. So that was also explained by Professor Piatnitsky. So you take a random variable, matrix valued random variable on the probability space with ergodic dynamical system, and then you simply define the random coefficients as the realization of that random variable. In that way, you can define the random operator A epsilon with the coefficients in this random field. And you can also look what happens with the solution of these resolvent equations for the convergence of the right-hand side. And then you can show in the similar way as in periodic case that the solution converge in L2 and weakly in H1 to the solution of the homogenized problem. And again, you can calculate the corrector, but this time you have to calculate it on the probability space. And the limit operator has the same form as original epsilon operator, and it is a differential operator with constant coefficients, where the formula for the homogenized matrix looks similar to the formula in periodic case, but here you average over the probability space. One of the differences is that happens is that this corrector, when you try to solve it, it is not satisfied that this corrector lives in H1 of omega, but it lives in something that we call nicely written H1 of omega. So you can look at it from the abstract point of view. You take the completion of the space H1 of omega. You look the completion of the space H1 of omega with respect to this semi-norm. And then you can show that corrector lives here. So the important remark is that Poincaré inequality is not satisfied on the probability space. And thus you cannot conclude that this corrector actually is in L2 omega. You can only conclude that its gradient is in L2 omega. So this is the difference. What about the spectrum? In both periodic and stochastic setting, when you have strictly coercive matrices with controlled constants, in the whole space setting, we have that the spectrum of the limit operator is always the whole positive real axis. It is simply the differential operator with constant coefficients. And also the limiting spectrum is whole positive real axis, because we can argument that the spectrum of the limit operator is always contained in the spectrum, in the limiting spectrum. Now, let's say something about periodic high contrast homogenization. Imagine that you have the material, which is also periodic, but this time you put soft inclusions. So these cells Q0 are inclusions, and the coefficients there are epsilon square, where epsilon is the size of inclusions. You can say that the matrix is simply identity, and outside we put a fixed constant matrix A1. So S0 epsilon is simply this set of inclusions, and S1 epsilon is matrix. Of course, you can also show that this kind of defined operators admit homogenization, but however, since the problem is degenerate, the limit operator has two-scale nature, right? So what happens is that since you have here very small coefficients, the solutions can oscillate on these inclusions. And so the limit operator is given on the space H1 Rn, and this second part models the possible oscillations on these inclusions. And thus this limit equation, you can write it as a coupled system. The second equation is given on the inclusions, and somehow this system is coupled, but it's, in a way it's weakly coupled, because in the second equation you can take x as a parameter, right? Because u0 depends on x, but the equation is given in the variable y. And then the first equation, you take the mean value of v, and you look and this given in the variable x. And this is the limit operator. And what is A1 home? Well, A1 home is the matrix that would come also if you would look the problem, the perforated domain. So you can write the similar formula. It's the same. You can write the similar formula for A1 home as we did in periodic case. Now I want to say something about band gap structure of the spectrum in high contrast problem. So if you write the spectra formally, the spectral problem for the limit operator, then again you have a coupled system. And the way you can solve this, you imagine that U0 is known in the second equation, right? Because X is only parameter in the second equation. You imagine that U0 is known in the second equation. So the solution of the second equation is given by this formula, where this function B is given on the inclusions, right? Because you first solve it, it solves this equation, right? When U0 is 1. And then you simply multiply it by U0. So you solve the second equation, you plug that solution in the first equation, and you obtain the equation of the following form. And this B beta periodic is something that we call Zhikov beta function. And it will be nonlinear function in lambda. And it can be calculated simply from this observation in this way. So here, these brackets mean that you take the average over the inclusion Q0 of the function B. And if you want to express the solution of this equation by eigenvalues and eigenfunctions of the Dirichlet Laplacian on the Q0, you can compute that this Zhikov beta function is given by the following expression. Here, nu yacht and phi yacht are eigenvalues and corresponding eigenfunctions of the Dirichlet Laplacian in the inclusion. Phi brackets are again denoting the mean value in the inclusion of the eigenfunction phi j. But here in this expression, you will see only the eigenvalues for which it is valid that at least one eigenfunction corresponding to them has non-zero mean over the unit cell. So if this is 0, then these eigenfunctions will not come into the expression, nu j. So, and then you can show, since you obtain this equation here, you can show that in the whole space setting, the spectrum of the limit operator is given by all positive numbers, non-negative numbers, such that the Zhikov beta function is greater or equal to 0. And then also this nu j prime are in the spectrum of the limit operator. These are eigenvalues whose corresponding eigenfunctions have 0 mean. Or since this set here contains also, since this first set here contains also all nu j, this set is equal to the set that you also include this first set, and you include here a whole spectrum of the Dirichlet Laplacian. In the bounded domain setting, you have to intersect this set here with the spectrum of this operator, which is nice in the bounded domain. It is a positive operator with compact resolvent, and thus its eigenvalues are increasing sequence of positive numbers that goes to infinity. So if you want to see how typical Zhikov beta functions looks like, it is like this. So here are nu j, right? And always at one side, so the domain is union of intervals. Always at one side of the intervals, it goes to minus infinity. At the other side of the interval, it goes to plus infinity. And so where it is positive, it's here, right? This is these red lines. And so the spectrum consists, the spectrum of the limit operator in the whole space setting consists of these intervals, right? And here, additionally, you have these points nu j prime. And if you are on a bounded domain setting, you would have to intersect this Zhikov beta function with increasing number of lines that goes to infinity. And thus, you would still have the limit operator in the bounded domain would still have countable number of eigenvalues. But however, this set would have infinitely many limiting points, namely all new J are limiting points of the spectrum, right, in the bounded domain. Now we want to say something about operators with stochastic high contrast coefficients. And first, we want to say something about how do we model random inclusions. So this time the randomness is given in space by putting different inclusions at different positions. So you have your probability space, and then you take a subset. We will give concrete examples in the following slides. You take a subspace of the probability space, and then you define the set of inclusions as the set of all x in Rn such that Tx of omega is in the set O. And so to obtain in the epsilon version, you simply scale this set. And the matrix is given by the complement of that set S0 epsilon. And then again, you can look the resolvent equation for the high contrast operator with stochastic inclusions. And then again, by using the version of two-scale convergence adapted to this stochastic setting that was introduced by Pyatnitsky and Zhikov, stochastic two-scale convergence, you can again show that the limit operator is has two-scale nature, and but this time the second equation you have to solve on the probability space, more precisely on the set of omega. So in the periodic case, you have to solve this on the unit cell. Here you simply have to solve this on the set O. So let's give some examples how you can construct probability space set O to model the random inclusions. So for example, take a sequence of IID, random. So the first one we want to model is, let's say you divide your plane into the unit cubes, and then at each cube you decide whether you will put the inclusion or not with some probability. So I will show the picture later. So first you take a sequence of IID random variables that take values in 0, 1. So 0 means I will not have the inclusion, 1 means I will have the inclusion. Then you take the probability space that contains these random variables, for example, by Kolmogorov construction. And then on this probability space, there is a natural shift that is ergodic, but this is discrete shift. And now, so this is how you model how you will put inclusions. So at each cube you either put or not put the inclusion, and now you have to move your origin in the unit cell. So you somehow randomly put your origin somewhere in the unit cell. So you enlarge this probability space with probability space given by the unit cell and Lebesgue measure on it. And then you can do it, and then you can define a continuum version of this discrete dynamical system, which will still be ergodic. So what is the set O? The set O consists of all the members of omega where omega 0 is 1, meaning that the cube neighboring to the origin will have the inclusion. I will show the picture on the next slide. And Y has to be in the inclusion. You take one fixed inclusion, let's say a circle. And then you can characterize fully how the space H10 on O looks like. So it consists of the functions. So for each omega, such that omega tilde 0 is 1, you take a function that is given on the inclusion. Okay. So you can take that here omega tilde is fixed, and then you choose a function from the inclusion, and it is defined only on the inclusion, it is 0 otherwise. And then you can see that its probabilistic gradient, it's simply its physical gradient taking on the inclusion. To show the picture of this, so here on this picture you see that so this corresponds to the following: omega tilde 0, 0 is 1, meaning that this cube contains the inclusion. Here omega tilde 1, 0, here omega tilde 2, 0 is 1. omega tilde 1, 1 is 0 because this cube does not contain inclusion, and so on. And the y is simply telling you where is the position of your origin. Here is the position at 0, 0, while on this picture, the position of the origin is at 1/2, 1/2. Okay, and so in this way, by doing this construction, so that you choose subset of omega, and then by doing constructing this space as 0, you can in this way you can model the random set of inclusion. This construction is already given in the book of Zhikov, Kozlov, Olenik on the homogenization. The second example that we want to discuss a bit is similar to the first one, but this time you can decide always to have the inclusion and to decide randomly its radius, right? So you take a fixed you take a fixed set Q0, which can again be taken to, let's say, a circle, and then you scale it with R. But this time, omega tilde j is a random variable that will tell you what is the radius of this. So you scale this Q0, and what is this radius of scaling, right? And again, the set O is simply, so we here also allowed the possibility that there is no inclusion by giving the possibility to this random variable to have value 0. And again, the set O can be given by all omega tilde. You again enlarge this set with unit cell and Lebesgue measure on it. So, and then the set O is defined as the set of all omega tilde jy such that omega tilde 0 is different than 0, and y belongs to this scaled inclusion. And again, you can characterize in the similar way, you can characterize what would be the space H10 on O, and it consists in the similar way as the functions that are in H01 on the inclusion, if inclusion exists in that cube. And the probabilistic gradient is simply the physical gradient of that function. So this is the example here. Omega tilde 0, 0 is simply telling what is the radius of this inclusion. Omega tilde 1, 0 is simply telling what is the radius of this inclusion, and so on. Okay, so this is about modeling and you can imagine even more stochastic examples where you put random inclusions according to some, let's say, Tint Poisson process. Put randomly, you don't have to follow this structure of dividing the plane into the cubes, right? So let's now speak about the Spectra problem for the homogenized operator, right? So we already wrote what are the limit equations on the probability space. Let's formally write the Spectra problem. So in the similar way, if you write it, you can solve the second equation by using this stochastic version of B function, which is now given on the subset of the probability space O. And then you can now define a stochastic version of Zhikov beta function, which would simply be, instead of taking the average of the unit cell, you take the average over the probability space. And again, the spectrum of the limit operator in the whole space, so this is the spectrum of the limit operator, not the limiting spectrum, is given by the positive numbers where this Zhikov beta function is greater or equal to 0, union the spectrum of Dirichlet Laplacian. What happens here is that the spectrum of Dirichlet Laplacian, so Dirichlet Laplacian does not need to have any more compact resolvents, so the spectrum can be continuum set. And in the case when S is bounded, you have to intersect this set with the spectrum of nice operator with the compact on the bounded domain, so constant coefficients positive operator with compact resolvent. So if you want to see the example 1, what happens? So Zhikov beta function looks in the similar way. You put some additional weights that come from the fact that that you either put or did not put the inclusion. And so it has the similar structure. The second example, when you change the sets of inclusions, is a bit more intriguing, because here you have the possibility of having this part here, which would also appear on the finite domain, the continuum spectrum, right? And what is also interesting here, so you here also take the average, but this time you take the average over the probability measure in the interval R1, R2. And what is interesting here, you can also destroy the structure in the sense that you have one, it will still, Gico beta function will still be increasing, but it doesn't have to go to plus minus infinity and so on. So this can happen. You have this additionally guys that appear here come from the fact that the spectrum of the Dirichlet Laplacian does not have to be an increasing sequence that goes to plus infinity, but it can take the values in some interval. Okay, now let's say something about the properties of the spectrum of the Dirichlet Laplacian and the properties of the stochastic version of beta function. So it can be shown if you take fixed omega, and you look the spectrum of this all possible inclusions that appear for that omega, and then you look the spectrum of these inclusions, you take the union over, so you take this should be deleted. You take the union over, so for one fixed realization, you take the spectrum of the Dirichlet Laplacian, you take the union over all k, or possible inclusions that appear in the realization, and then you can show that almost surely this set is a constant and that this set corresponds to the set of the Dirichlet Laplacian. Moreover, if you take one fixed typical omega, and if you can define, and then you define this solution, this B function on a physical set, so it is actually defined on the each inclusion separately, right? So you calculate the standard B function for the periodic media on each inclusion separately, right? And then you lift it up on the probability space. Since this problem is somehow translationally invariant, you can show that this, if you take, so you define this function, you take its value at the origin, but then you can show that every other value is simply the realization of this function. And that this function that you constructed out of one typical omega is the solution to the following, so you decided from all omega, I'm sorry. This is the solution of the following equation on the set O. So this is how you can express, also by using this observation, you can see that you can express Gico beta function by using the Ergodic theorem in the following way. So you take a realization, you take this B tilde function for that realization, and then you simply, instead of taking the average over the probability space, you use the Ergodic theorem here. And again, you can show in general that the derivative of the stochastic version of Gico beta function is greater or equal 1 minus the probability of the inclusion. So for example, so if you look this formula, so somehow you can construct Gico beta function out of one typical realization, which is something you expect since you have ergodicity in the background, right? And then you can characterize also, you can characterize the point spectrum of the homogenized operator, and it coincides with the point spectrum of the Dirichlet Laplacian, whose elements have eigenfunctions with zero mean, right? So you can completely characterize the point spectrum. So if you look the spectral problem, then you can easily see if you take, I'm simply here giving the argumentation that the right-hand side is a subset of the left-hand side. So if you take the lambda that is in the point spectrum of the Dirichlet Laplacian and has a zero mean eigenfunction, then you can easily see that U0 equals to 0 and U1 equals to y psi lambda clearly satisfies 1, because if you take the second equation, U0 is 0, psi lambda is simply the eigenfunction for lambda eigenvalue. So this is satisfies, and here both sides are 0 because U0 is 0 and here the mean value is 0. So and you can argument that also the other inclusion is also satisfied. Now, let's say something about the limiting spectrum in the case where S is bounded. In the case where the domain is bounded, the limiting spectrum converges to the spectrum of the limit operator in the sense of Hausdorff, meaning that for every member of the spectrum of the limit operator, there exists a sequence that belongs to the limiting spectrum, that belongs to the spectrum of A epsilon, such that lambda epsilon converges to lambda. And if you have a sequence of eigenvalues such that lambda epsilon belongs to the spectrum of A epsilon, which converges to something, then lambda is necessarily in the spectrum of the limit operator. Let me just say that the first property directly follows from the strong two-scale resolvent convergence, which you can prove by using stochastic two-scale convergence in a standard way. So the first property you have, but somehow for proving the second property, you need something more. So in the case where S is bounded, you can look the spectral problems, and then you need somehow to assure that these eigenfunctions are not converging to zero, and you can indeed prove the compactness that U epsilon, if you take eigenfunctions that corresponds to the sequence lambda epsilon, then U epsilon converges strongly to scale to some function U, which is then different to zero, and then this function U has to be the eigenvalue of the limit problem. You simply pass to the limit in this equation, right? And so you obtain also the second claim. But to obtaining the second claim, you need something more than simply proving strong two-scale resolvent convergence. Now, in the whole space setting, you still have strong two-scale convergence of the operators, which you again prove by using stochastic strong resolvent convergence of the operators, which you again prove by using stochastic two-scale convergence. But we will see that this set, so the spectrum of the limit operator is always subset of the limiting spectrum. And in example one, we will argument that the spectrum of A epsilon is always whole positive real axis. So its Hausdorff limit is positive real axis, and it is different than the spectrum of limit operator, which was given by this Zhikov beta stochastic beta function and had band gaps, right? And in example two, we will argument that the limiting set, the limiting spectrum is equal to union of all possible periodic spectrum for all possible radii that appear, in the interval R1, R2, of course, that have positive probability. So you need to look the support of the probability measure on this interval. Union these additional eigenvalues. So you need to take into account all possible periodic media with radius R, and R lives in the support of the probability measure. And we will somehow argument that Weyl-type sequences for this set, so for the set that is in the limiting spectrum, but not in the spectrum of limiting area, lives in non-typical areas, what we will explain later. Now, let's say about the assumptions. So this result about characterizing the limiting spectrum, we will obtain only for finite range correlations. And let's say that we put some natural assumptions on the set of inclusions. I will explain it on the picture. So here you have the set of inclusions, but you additionally assume that there exists some kind of extension domain outside these inclusions, and these extension domains are disjoint from each other. They are distanced with a fixed constant from each other, and they satisfy some kind of minimally smoothness assumptions, delta NM property. You can find this in the Stein book, how to construct the extension operator. So what is needed is that you need to somehow construct the extension operator with controllable constants. So with this minimally smoothness, delta NM smoothness, with prescribed constants, you somehow control the constant in the extension operator. So they can be Lipschitz, but in a way you have to control their geometry to be able to construct the extension operator. So this also you need in the finite domain setting, this kind of control on the geometry of the inclusions. But additionally here in the whole space setting, if you want to characterize the limiting spectrum, we somehow impose finite range correlation, meaning the following. There exists K in R plus such that for every two compact sets with the property that are distanced at least K, the distribution of the holes of K1 is independent of the distributions on the holes on K2. And this is stronger than ergodicity. And this you need, so this property will be needed for the construction of non-typical areas, which we will now comment soon. Now we define, yes? Okay. Now we define the new beta function, which is, and the difference with respect to this beta function is that you take supremum. So in the original stochastic beta function, you would take the limit here, but here additionally you take supremum over all x in Rn, and then you take the limit. Right, so visually it's a subtle difference. So the difference is simply taking supremum before or after the limit, but actually the difference is huge. In example 1, the beta infinity function will be simply the maximum of lambda and taking the periodic beta function for inclusions that were circled. In the example 2, the beta infinity of lambda would be maximum over all radius, taking all possible periodic beta functions for all radius. And what we can show is that limiting set is characterized by this limiting by this beta infinity function, and not with this stochastic beta function that was appropriate for bounded domains. I will simply comment why this happens, that beta infinity functions looks like this. Why is in example 1? So in example 1, you have arbitrary large areas that exist consisting only of no inclusions. And thus, when you take supremum, since these arbitrary large areas exist, you have to take the possibility of having no inclusions in this formula. Also, you have arbitrarily large area only with inclusions. And thus, the beta infinity function here is the maximum of these two possibilities. In the second example, you can have, if you only have inclusions, you can have still arbitrary large area with having, almost surely you have this kind of areas, with having balls of radii in R minus epsilon, R plus epsilon, for epsilon arbitrarily small. And somehow the existence of this large area that are almost periodic, and then you can construct the wave sequences for the limiting set, right? If you want to characterize the limiting set, limiting spectrum, you can construct the wave sequences that live only on these non-typical areas. And thus, the corresponding limiting points would be the one that come, since these sequences live on these non-typical large periodic areas, the limiting points will be the corresponding limiting points of the periodic domain. Okay. And now I will go to the conclusions. We analyzed spectrum on media with random high contrast inclusions. In the case when we look the bounded domain, we can do the analysis in the similar way as Zhikov did for bounded and unbounded periodic domains by using stochastic two-scale convergence introduced by Pyatnitsky and Zhikov. However, random inclusions influence significantly Zhikov beta function, and continuous spectrum can appear in the limit operator, even on the bounded domain. In the case of whole space setting, it always happens that the limit spectrum is different than the spectrum of limit operator, unless the medium is purely periodic. This happens as a consequence of law of large numbers and existence of non-typical areas on whole space setting. We are able to characterize the limit spectrum in the case of whole space setting by introducing the new version of Zhikov beta function for whole space. And the last remark I did not have time to explain. So thank you for your attention.
Thanks very much for your interesting lecture. Some questions, some remarks, comments?
I see.
Yes. You can read, Igor, the chat in the chat.
Yes. Okay, I can share the slides. Do you need an hypothesis for the interparticles distances to perform the homogenization presented in the beginning? If you mean fixed distance for this extension domain, yes, we need it in order to be able to construct the extension operator, right? And this is somehow without it, we don't know how to do it, right? But if you are thinking on this finite range correlation, we don't need it for the bounded domains. Stiff inclusions is a completely different problem. It would be possible to do something, but I didn't look at this problem. Okay.
Okay, thanks. Any other question? No, okay. I thank you very much again. And I think we resume by 20 minutes. It's okay, Nanda?